Okay, so for this question, a block of glass of mass 5 kilograms, temperature 30 degrees Celsius is brought into contact with a block of asphalt of mass 20 kilograms and a temperature of 75 degrees Celsius. Specific heat capacity of asphalt is twice that of glass. Take note. And no energy is transferred to the surroundings. What is the final temperature of both blocks? Okay, so a lot of concepts involved here, but we can begin this problem by listing out the information that we know. Okay, so we know that the mass of the glass is equal to 5 kilograms. Okay, we also know that the temperature, okay, is equal to 30 degrees Celsius. Okay, as for the asphalt block, it is 20 kilograms and its temperature is 75 degrees Celsius. Okay, so for problems like this, it's important to just write down what you have so you can easily see. Okay, at this point, it's pretty obvious that the temperature of the asphalt is greater than that of the glass. Okay, so this will come in handy in a moment, or at least in your conceptual understanding of this question. Okay, we are talking about specific heat capacity as well. It does talk about that. It mentions that. So what we can do here is we can set it up a certain way. All right, remember that whenever you're talking about energy, specific heat capacity, we have a formula associated with this. Okay, this is Q equals mCT. All right, do I have M, which is the mass? Yes. Do I have your specific heat capacity, C? Well, we do have information about it. Okay, do I have the change in temperature? Well, it does give us information about temperature, and it is asking for the final temperature at the end. Okay, so one more thing you need to know here is, for a problem like this, the energy lost must equal the energy gained. Okay, you'll see that in a moment. Okay, so let's begin with setting our equation, or setting up our problem. So we have the mass of the asphalt multiplied by its specific heat capacity. Okay, do we know what that is? No. Okay, we do not know the specific heat capacity of that. Okay, however, and in terms of our temperature, okay, we have the temperature of asphalt minus that particular temperature we need to figure out. And I'll explain this to you in a moment. So just hold on. I'll write this down. This is for the glass. Specific heat capacity of the glass, T minus T of the glass. Okay, so what did I just write here? I literally just set the two equations for for Q equal to each other. Okay, this is for asphalt, this is for glass. If you recall, once again, the formula, Q equals mc change in temperature. Okay, this is my basis, and I'm setting it up equal for both because we have two objects involved here. We have the block of glass and we have the block of asphalt. Okay, the question you might be asking is, why here am I doing TA, the temperature of asphalt, minus temperature, and then here I reversed it, I switched the order? Well, as you can see, the temperature of asphalt is greater, okay, than that of glass. Now, why is that important? In class, we talked about thermal equilibrium. Okay, thermal equilibrium. So if I have two objects of different temperatures coming in contact with each other, okay, eventually the two temperatures will kind of meet in the middle. Okay, so that means my higher temperature will decrease, it will get lower, and the lower temperature will increase. Okay, at least I'm just talking about numbers here. Okay, so for example, 75 should end up at a value lower than 75, and then 30, okay, if it kind of compensates or meets in the middle, should end up becoming at a temperature a little bit higher than 30 degrees. So in that case, this particular temperature here must be less than that of asphalt, because asphalt is my higher temperature. Okay, whereas here on the other side, the temperature of glass here must be lower than that particular temperature, if that temperature were to be in between. Okay, so if you want to further imagine that, it's like the temperature that I'm looking for, okay, must be in between the temperature of asphalt and the temperature of glass. Okay? So that is the reasoning behind this setup. Now, we're not yet quite finished. We need to take note that the question is telling us that our specific heat capacity of asphalt is twice that of glass. Meaning, instead of writing specific heat capacity for asphalt, I can rewrite that in terms of that of glass. It's twice that of a glass, so this is going to be 2Cg. Okay? I'm doing that so that I can simplify my problem. Okay? And everything else can be practically the same at this point. Okay, well, now I can narrow this down further by substituting the information that I know. Okay, I know that the mass for asphalt, the asphalt block, is 20 kilograms. Okay, 2 Cg, the temperature of asphalt is 75, minus that particular temperature that we don't know, equals the mass of glass, which is 5, okay, particular specific heat capacity, the temperature that we don't know, and the temperature of gas, which is, or glass, sorry, which is 30 degrees Celsius. Okay, now here you can already see that we can cancel out our specific heat capacities, okay, and just solve this. So 20 times 2 is 40, and here I'm left with 75 minus t. 5, this becomes 5, and then t minus 30, okay, and this is just going to be math moving on. So 40 times 75 is 3,000, okay, minus 40t, this is the distributive property. This is 5t minus 150, okay, and then move things around. So this is going to be 150 equals 45t, okay, and if I divide both sides by 45, my t should equal 70, and there we go, we have our answer. Okay, so it seems lengthy, but really this portion of my solution, this is just algebra. Okay, the difficult part here is identifying how are you going to set up this problem. Okay, and this is a typical kind of question, a way of questioning that will appear under the unit for B1, thermal energy transfers. So it's really important to kind of identify, okay, and be aware of the concept of thermal equilibrium. Okay, when I have two temperatures involved with different masses and heat capacities, this is the one of the common strategies or approaches to solving a problem like this. Okay, now you have to be careful because common mistake is you're so invested in setting up the problem correctly that you make mistakes in your substitution. Okay, sometimes instead of putting 20 here, you end up putting 5 and you end up switching things. If you do that, I can tell you, the answer will end up becoming 45 degrees Celsius. And whenever you see 45, you might immediately think you're correct, not realizing that you did not substitute the right value. So please be careful of that as well. Okay, so that is how you would do a problem like this.